And at this break time, I can give a brief introduction of Professor Max Welling. Professor Max Welling is a research chair in machine learning at the University of Amsterdam and VP Technologies at Qualcomm. He has a secondary appointment as a senior fellow at the Canadian Institute for Advanced Research. He is on the board of the Data Science Research Center in Amsterdam. Uh,
You tell me when to start, right?
yeah, it's time. You can start whenever you
Okay.
want.
Right.
Thank
All
you.
right. Thank you very much. Yes, so I cannot really claim I'm a expert in causal inference, and certainly not in causal inference in computer vision. But I do want to talk about two papers that we wrote in this field of causal inference, and I hope you enjoy. So this is work with these amazing co-authors. So the students for the first paper I'll discuss, which is amortized causal inference, are Cindy Leeuwen and David Madras, both shared first author. And then the student for the second paper is Maximilian Ilse, and that paper is about causal reductions. Now, so this is basically precisely the same message as Sunjung was talking about. It is not easy to publish papers in deep learning based in basically deep learning based methodological papers on causal discovery. And that's similar to, I'm sure, causal discovery in computer vision. I think we see a sort of a split of a community. There is a bit of resistance in the causal inference community to this type of more methodological work. And I think that's a pity. And I want to plea, that's the dog. Dogs can plea very well. If you have one, you know. I want to make a plea for fostering both theory and methodology. For instance, in deep learning models in causal inference. In other words, more data-driven work, more competitions, new data sets, etc. Clearly, these things have propelled the field of computer vision in the past and also natural language processing. I think theory is important, but it should live next to more empirical and methodological approaches. And I think if we embrace it, then it will actually accelerate the field forward. And so, if need be, I agree we should create our own community and our own conferences in this field. So the first topic I want to talk about is Granger causality. And so we say that a variable x that evolves over time, so now we use time information, Granger causes another evolving variable y. If the predictions of the value y based on its own past, um, and on the past values of another variable x are better than predictions based on y's past only. So in other words, if you can improve the prediction of a variable y by also looking at another variable x, then we say that that x variable causes y. Of course, we look at the past of those variables x and y. So in this case, we explicitly use temporal information, but we do use temporal information in real life, so that's not so strange. The model we will follow is a VAE style amortized encoder decoder model to basically directly infer the causal interaction graph using a deep neural net. And in fact, the net is a graph neural net, like the neural relational inference model that we developed with Thomas Kipp in the 18. So what do people do so far, even until very recently? They basically treat every new problem separately. So these, for instance, you have a bunch of particles. Some particles cause other particles, have causal interactions with other particles. Then you study the time sequence and you learn sort of a model with parameters and you put sparsity priors on these parameters. And the parameters that survive are the parameters basically that actually influence the future time series of another variable, very much the way that Granger causality works. The only problem with this is that if you have a whole family of related problems, even though the interactions might be different, they do share information. And so it's a bit of a waste not to learn or combine statistical strength between all of these models. And that's precisely what we propose. It feels not a big step, but surprisingly, nobody has done this. So we basically say, well, let's feed all of these separate problems with different causal graphs and different interactions into one amortized encoder function that then predicts for each of these independent problems, predicts the causal relations between the different variables, which could well be different for each one of these instances, of course. Okay, so the encoder is very much like a the encoder in a variational autoencoder. It's like an amortized function. So we take time sequences x1 to xt and different time sequences I, j, etc. We feed them into an encoder, and the encoder is going to predict as its output the causal relations between every pair of variables. So in other words, you can be directed in one way, in the other way, there could be no interaction, or there could be interaction in both directions. And so there's also a decoder. The decoder then takes the time sequences as well as the inferred causal graph. And so here's the time sequence. We input the tth point, which is the point where we want to make the prediction. And then we predict forward the future time series, t plus 1, etc., for each of the time series using a decoder model. And then, since we do now in the training set, we do know these time sequences, we can then backpropagate to train the models both of the decoder as well as the encoder in the usual way as we do in a variational autoencoder. So in slightly more detail, of course, because it's a variational autoencoder, we can write down an elbow. And the elbow is again the expected log probability of the decoder model minus the KL term between the prior that we have over causal relations and the posterior. Now note that causal relations are actually discrete, so we will need some kind of Gumbel softmax trick to learn. Now, how do the models look in slightly more detail? We use a mean field approximation for each one of the latent variables z, so it's a product over each one of them. And we use a graph neural net, very much similar to the neural relational inference model that we developed in 2018, to basically set messages over the complete graph. So in this case, we haven't inferred anything yet about the graph, so we set messages over the complete graph. And the decoder is also some kind of graph neural network, but now the messages are being sent only over the inferred nodes in the graph. So it's going to be a causal model now. And we have basically a prediction of the mean, and then we sample so that the next time point from the predicted mean, and the mean was predicted by a message passing scheme a la a graph neural network. So that's basically all for the theory. Now let's do some testing. So here's some typical data sets. There's a bunch of particles. Some particles attract or repel other particles, and they are locked up in a box. Now let's look at training set size. So we have 3 models that we tested here. We have the model that's called ACD, which is the one I just described, which is just the amortized encoder. Then we have something else which we call test time adaptation, where we initialize with basically the encoder, and then we do some just non-amortized variational mean field updates on Q of Z, which is the distribution, the posterior inferred distribution over the latent variables, using the usual mean field updates. And that's not amortized, that's the usual variational inference. And then, of course, you could do both. Now, what we see, the most important thing here is that the performance really improves a lot, going from 0.6 on average all the way to almost 1 if we increase the training set size. And now the training set size are all different particles with different interaction types, being generated. They're not exactly the same model. We can also add unobserved confounder particles, dark matter, you could think. And on to the right, we make the problem increasingly hard, which is the number of the number of other particles which are directly influenced by that unobserved particle. And then if we just observe everything, of course, we get very good performance. If we just not take it into account at all, or we try to do something trivial like mean amputation, we see that the performance degrades very quickly. And if we do the right thing in our model, which is we reserve a slot for that particle, we use our decoder / simulator model to predict forward the trajectory of that latent particle, then we get pretty good performance. And then the supervised one is given by basically you treat it as unobserved, but you do know the sequence, and so while training, you can actually train it to infer the correct trajectories. And of course, that does a little bit better, but that's typically not what you have in terms of data. And so we do almost as good as the supervised scenario. So it can handle unsupervised confounders. There's also another problem, which is the Kuramoto, ODE, which is basically phase-coupled oscillators, like here. And here we see the same thing happening. If the training set size increases, our methods improve dramatically. The encoder model starts off being a little worse, but then when it starts to train, it actually surpasses all the other models, even the models where we do test time adaptation, which seem to overfit a little bit on the particular test set. And all the models that don't learn, which is all the traditional models so far, actually don't do all that well. So of course they start off equally good, or maybe slightly better, but then very quickly, they cannot improve because they don't learn from the other sequences. They get overtaken by sequences which use amortized encoders and decoders. We can also use it immediately on unseen test problems. So for a normal Granger causal model, you will have to retrain your model for every new test case. We don't have to do that. We just have an encoder, and we can predict immediately what the causal inferences are, and we get very, very good performance relative to the other methods. And we also tried it on a problem which is basically fMRI data sequences, which is the typical sample where the graph there's only a single causal graph, and so we basically use the usual setting for Granger causality, where we do test time adaptation, variation inference with QZ, and then basically we get on par with the best methods out there for the usual causal inference, Granger causal inference. Of course, our method shines when we have a family of problems that are related, and we can transfer knowledge from one problem to other problems. So the next paper I want to talk about is causal reductions. And here, so this is a paper with these co-authors here. In this paper, we do not use temporal information, so we just have a data set. And the motivation for this was that the global clinical market size value is about 44.3 billion. So basically, when we need to test new medication, we have to do all these clinical tests, and it's an extremely expensive process. And the question that we wanted to ask is, can we reduce the group size, so that the number of patients or people that are participating in these clinical tests, by including observational data and not just interventional data? Of course, a clinical test is an interventional test. It's not observational, but we do have a lot of observational data lying around. Now, the idea was to not assume anything about the confounder variables. So to have a very general assumption about the number of confounders and how they interact, but then try to reduce the confounders to a single variable and to a very simple graphical model that is what we call intervention equivalent. And again, deep learning is playing an important role here because we're going to use normalizing flows. The normalizing flows are being parameterized as deep neural nets, and we're going to try to train these models, jointly on interventional and observational data. Okay, so a little bit of a definition: the causal reduction of confounders. So what is a causal reduction? I'm going to just read out what it says here. So let M be a causal Bayesian network. like maybe you want to look at this figure here, let M be a causal Bayesian neural network with variables X and Y, and in such a way, and latent variables Z. And Y should not be an ancestor of X. Then there exists a causal Bayesian network M star with observed variables X and Y again, and a single latent variable Z that takes values in the same space as X, such that M star is interventionally equivalent to the original M with respect to perfect interventions on the variables X and Y. So for instance, this whole mess here needs to become equivalent to this very simple diagram here. And what we mean when we say the interventionally equivalent, we basically say that the model under M and M star have to have the same marginal on X and Y, and it have to have these same two interventional distributions on X and Y. And you can actually, the proof is actually graphical. So you can start with this mess. You can then basically first represent all of these Z's as a single high dimensional Z. We can then introduce W, which is a copy of X and is related by a delta function. We then merge W and Z, and then we change the variable in the other direction. So now it becomes PZ given W, PW. And then finally we marginalize out Z, and then we get this. And in each one of these steps, you can show its equivalent, and all of these relationships hold. So that to me was somewhat of a surprise that you can do this, right? So in some sense, you can assume very, very general stuff happening in terms of confounders, but you can reduce it to a model that's equivalent, at least interventionally equivalent, that is much more simpler, in which we can actually learn. Okay, there's one more theorem that we have to go through, but this one is somewhat trivial almost. It says that if P of X given Y is a Markov kernel, is just a conditional probability over variables X with components XM and an argument Y, then there exists an M-dimensional standard normal variable Z independent of Y and a deterministic map F such that X is F of Z and Y. Now, what does this mean? So if you're familiar with what people call reparameterization trick, in the reparameterization trick, you rewrite a probability distribution where sort of the stochasticity is sort of hidden. You pull out externally the stochasticity, like in this case it's a Z, and make it distribute according to some standard simple distribution. And then basically you write X as a deterministic function F, conditioned on this, as a function of the stochastic variable Z and this fixed variable Y, right? And this is nothing else as the sort of reparameterization trick. So then the previous diagram, which was this one here, and note this one is a deterministic node. It has a deterministic relationship with W. Now we can also create a deterministic variable Y that gets its randomness from an additional variable V. So this prior diagram can now be rewritten like this. So X is F of U, where U is the random variable, and Y is another function G of U and V and X. So this thing is now just equivalent to what we said before. So that's the observational distribution, the reduced observational distribution. And then this is, of course, the interventional distribution where we intervene on X, which means that all the incoming arrows will be deleted. So this is the observational, and this is the interventional distribution. So now the trick is to say, well, let's write down a new loss. And now the loss is like what you do in semi-supervised learning. You say it is the sum of the log likelihood for the observational data. It's a joint distribution of X and Y over the observational data, plus another sum over the interventional distribution, Y given do X, right? Where now these are the interventional data that you have collected. And since both of these models basically come from the same core, so they have the same parameters, so this relationship here has the same parameters as this relationship here, and also this relationship. Right? So these parameters are shared between these two models, and so now you would hope that if you use both of these models, you can do a little bit better than if you would only use interventional data. Okay, there is a generalization also to having observed confounders. So this is an observed confounder. You go through a similar reduction, you get to this one, and then again, you also make this node deterministic, and then you get to this one for observational distributions and this one for interventional distributions. So then little experiments that we did. So here we have the training data. The blue dots are the observational data, and the orange dots are the interventional data. We have, this is a model that's trained on 50 interventional samples. You can think of it as a clinical trial if you want, right? No, it reproduces pretty good the results of the interventional data. And then here is a model that's being trained on 50 interventional data and 1,000 observational samples, right? Because typically we assume we have lots and lots of observational samples lying around. Now, if you look at the log probability for the interventional distribution, py given do x, then the the accuracy, or sorry, not the accuracy, the error is coming down as we increase the number of interventional samples, obviously, you know, for the ones where we use these interventional samples in the model. So the blue curve is only interventional, and then the green curve is interventional and observational, which is the proposed model. And then this curve is only observational data, which of course will not improve on the probability y given do x. But you see that so we need less, by using observational data, which is the blue curve, we need less interventional data to reach the same accuracy, which is the effect that we want to achieve. And this is the same, but now for the conditional observational distribution, we also see a somewhat similar effect. I should say that this is somewhat cherry picked. There's also examples where this is less clear, this benefit. Now the question is, can we save money? So in other words, if we include observational data in our clinical studies, can we actually use less interventional samples? Now, if you read out this problem, this is a problem with 1,000 observational data. These numbers here are different data sets that we looked at. So these samples here are the ratio between observational and interventional samples. So this is the number of interventional samples that we're using. And this number here now says that a clinical trial with a group size of 200 interventional samples has the same statistical power as a group size of 100 interventional samples and 1,000 observational samples. So you're winning a factor of 2 here by using your 1,000 observational samples. And in fact, if you turn that into numbers, I think you can actually save billions of dollars annually in these clinical trials if we start to believe these types of models. Okay, so then to conclude, I've talked about amortized encoder-decoder models that can improve Granger causal predictions by basically pooling over a family of similar problems, but not identical problems. Another place where we apply deep learning to causal inference is normalizing flows applied to causally reduced confounder models, where we are combining interventional as well as observational data, and in that way cut the cost of clinical trials. And again, the message that resonates also with the previous speaker is we should really embrace deep learning in causal modeling and also allow, a rich sort of community that develops more methodological methods in causal inference. That's it. Thank you very much.
Yeah, thank you, Matt. Thank you for this insightful talk. So now maybe we have about 5 minutes for the QA session. So if there's any questions from the audience, please use the text box or just raise your hand. Okay, and I have a one-up question. Is that this talk is about how the causality helps with the deep learning, right? So I wonder maybe in some cases that causalities may help with deep learning, and maybe in some other cases maybe causality may not help. For example, maybe in out of distribution data, the causality may help, or maybe in distribution data, the contribution of causality may be not so so big. So could you give us some sense about when and how can we use the causality to help with deep learning?
Yeah, so that's a slightly different question than I talked about here, because here I was talking how deep learning can help, trying to infer causal relationships. You're asking how causality can
Yeah,
help build better causal models in order to generalize better, let's say.
yeah,
Yeah, so I can only repeat what other people say, and with which I really agree. So if the so the if you really find the true causal mechanisms in a model, then they are much more robust and stable if you change from one domain to the next domain. So the idea is that causal mechanisms are sort of they only change sparsely. So most causal mechanisms are stable if we move from one situation or context to the next context, which means that we can use them for generalization better. In general, I would say if your generative model, you should have a generative model and an inference model, both of them living together, like in the VAE. In your
mhm,
generative model, you really want to put your causal relations in your physics, because and the better that model is and the better it reflects the real world, the better that generative model will be. And then the inference model should be sort of the approximate inverse of that generative model. It should go from the data directly to predictions. And if you constrain that to be the approximate inverse of the generative model, then I think it will do better if the generative model will have these causal relations in it.
okay. Thanks for answering me. And there is another question in the chat box. Can you see it?
Oh, I need to open it.
Yeah, it's about the question is why using
Yeah.
normalizing flow rather than the other common generative model in the proposed pipeline, such as normal VAE?
Yeah, I think that's a good question. I think we could have used a VAE as well, but there is this very nice deterministic relationship between, the random, so it sort of went very well with the causal reduction derivation, right? Because in the causal reduction derivation, we ended up with a deterministic relation between a random variable and x, which was, coming out of it. And maybe I can go back to it. Let's see if it's easy for me to go back. Let's see. So here, oh, can you see it?
Yeah, yeah.
So in this place here, you can see that by going through these causal reductions, we ended up with a variable and a deterministic relation to x, which is, and also w in this derivation has the same dimension as x. Basically, that's what we state here, that the variable, sorry, actually that's in the next page here, that the z variable here has the same m-dimensional variable as the original variable x. So in this particular way, the w and the x are already somewhat of a flow, right? And so the only thing we did in going to this setting is to say, well, this part we already had from the causal reduction. Now we just also make this a flow. We just externalize. The only thing we do is we just externalize the randomness, and that's kind of convenient. And then you have basically already written down something that looks a lot like a flow, and it's very natural to then model everything like a flow. I should say you could do something else. You could just start with this model, and you can just turn everything into a VAE like model, and you can do things there probably as well. But it turns out what you end up with your causal reductions is already almost like a flow, so it's a very natural step to take.
Yeah.
I see another question coming in. Oh no, it
Mm,
says got it. Thank you. Yeah.
yeah, I think there's no question from the audience. So thank you again. Thank you, Max, for giving us this excellent talk. Thank you very much.
Thank you for inviting me.